Continuing with our exploration of light, we now put this in a graphical form. Remember I said that light is called electromagnetic wave. And again, that was to highlight the fact that light is created by interacting electric and magnetic fields. And we said that light comes in different sizes that we termed wavelengths, and that there were frequencies associated with different wavelengths. Also remember that there was a relationship that if you took the frequency and multiplied it by the wavelength, that it equaled the speed of light. That's going to be very important in a second. If we take all the various forms of light that exist in nature, we can list them in order of wavelength or in order of frequency. Sometimes you will see long wavelength on the left and short wavelength on the right, like in this diagram, or sometimes you'll see the exact opposite. So try not to memorize one particular way. It's always better to understand it than memorize it. If we look this way, with the longest wavelengths over on the left and the shortest wavelengths over on the right, we see that visible light is here in the middle. And visible light we can subdivide into the colors of the rainbow. Hopefully you've heard the acronym Roy G. Biv. Roy G. Biv stands for red, orange, yellow, green, blue, indigo, and violet. Those are the colors of the rainbow. So red is the longest wavelength of visible light, and violet is the shortest wavelength of visible light. Now there are wavelengths that are too long for your eye to see. They are longer than red. We call those infrared. You might know infrared from heat lamps if you've worked in a restaurant, or if your bathroom has one of those funny red light bulbs in the ceiling that puts out heat when you get out of the shower. That feels really good. Longer still than infrared is what we call microwaves. For example, in a microwave oven. Now you don't actually see the microwaves bouncing around in your microwave oven, but you can definitely see the cheese bubbling on top of your nachos. Longer still is what we call the radio end of the spectrum. And I know that you associate radio with sound, and that's because there's this device that we call a radio that actually takes this very long wavelength form of light and converts it through this machine into sound. So radio is technically a form of light. So the radio end of the spectrum is the very long wavelength end of the spectrum. Some of these wavelengths are as large as a football field. Going to the other side, if we go again to visible light, the shortest of the wavelengths of visible light is violet. There are wavelengths that are too short for your eye to see, just beyond violet. We call those ultraviolet. You're familiar with those because those are the ones that you use sunscreen to protect yourself against because they can give you sunburn, and if you're exposed to too many over too long a period of time, leads to skin wrinkles and skin cancer and cataracts and all sorts of nasty stuff. Shorter still is X-rays. X-rays can actually penetrate the soft tissue of your body. But remember that you should limit, no one gives themselves X-rays for ha-has, right? Except for, maybe in graphic novels when you want to make a superhero. If you're getting an X-ray, the technician will always ask, if you're a woman, if there's any chance you could possibly be pregnant. And then they hide behind a screen so that they don't get zapped with the X-rays. So you should limit your exposure to X-rays. And then shortest of all are the gamma rays, and nobody wants to be exposed to gamma rays. There is no good use for gamma rays. Gamma rays are what you find not only in science fiction, but in nuclear reactions. The high energy rays that are just very, very bad for you can cause cancer. So hopefully you're seeing this relationship that the shorter the wavelength, the more dangerous it is. And the longer the wavelength, the more benign it is. Now remember that the frequency times the wavelength equals the speed of light, which means that as the wavelength gets bigger and bigger and bigger, the frequency has to get smaller and smaller and smaller so that they balance. Similarly, as the wavelength gets smaller and smaller and smaller, the frequency has to get bigger and bigger and bigger to compensate. So the radio end, which we sometimes call the red end, is characterized by long wavelength, low frequency, and low energy. These are not dangerous waves. And the reason why they're not dangerous is because energy is proportional to frequency. So if you have low frequency, you have low energy. Conversely, the gamma ray end is called the blue end, the short wavelength end, high frequency end, high energy end, dangerous end. In astronomy and all of sciences, we sometimes make approximations, and these approximations allow us to make the math easier, to make a model to study something. And so there's a kind of a hypothetical object that we use in science called a black body. A black body is a hypothetical object. It is a perfect emitter of energy. It is a perfect absorber of energy. And it's a hypothetical object, but it turns out that stars are really good approximations. And there are some really important properties that black bodies have. There are two really important laws that black bodies follow that we use in astronomy, and these are called the Stephon Boltzmann Law, which deals with the luminosity or energy output, and Wien's Law, which deals with the temperature. And I'll be discussing those in more detail when we look at the mathematics behind this week's lessons.